Hi, I'm Ali Brown, Director of Graphics Engineering here at Cloud Imperium Games, and today we're going to be talking about Gen 12, our new multi-core renderer. In addition to myself, we'll also be hearing from Christopher Bolte, our core engine architect, and Darryl Barnes, our graphics programmer. And today we're going to be talking about the need for our new renderer, the architecture and how it's built, Vulkan, which is the back-end API we use, and the progress of how we're doing so far, and then what's next for the graphics team. So, to help understand the need for the Gen 12 renderer, I first want to take a look at the high-level structure of our existing renderer to try and understand how the new renderer will differ. So here you see a diagram, very simplified, of our overall architecture, and on the left-hand side you can see the 3D engine, and this is what manages all the visible objects in the scene, for example, their position, their size, and ultimately is responsible for the culling of them objects and deciding what should be sent through on-screen each frame to the renderer. And obviously the job of the renderer is just to feed out the image at the end of the frame. And to do this, to manage this process, all of these objects have to pass through this single universal pipe, this conduit of information in the center. And as a result of that, every object has to come through with a certain amount of settings or paperwork and baggage to describe how they should be configured, and it's represented on the diagram by these switches. So this type of design initially seems very flexible. Having this universal pipe, you can very easily toggle certain settings and get a very different rendered result for each object. But the reality is actually that the objects and the renderer both end up extremely complicated because they have to decipher this list of instructions and distribute these objects through the various pipelines and stages inside the renderer. And this has to happen for every object, every frame, and this deciphering ends up resulting in quite a significant performance problem. And it also makes the renderer quite inflexible because it's quite complicated and hard to change the architecture. So how does our Gen 12 renderer differ from this? Well, the methodology we're taking on is to try and make everything as explicit as possible. And we're trying to minimize all these redundant connections and switches and configuration options and try and get things much more streamlined. So to do this, each object in the world will directly communicate with the render pass responsible for drawing that object at startup time. So when the object is first spawned, it will communicate directly with the pass responsible for it and pre-configure everything possible at that stage. Now, this has a bunch of benefits. So by speaking directly to the thing that's rendering it, it doesn't have to worry about all the other rendering systems. So we end up with a much more limited set of parameters, both on the object and on the rendering pass. And all of the settings we do have are very relevant for the task, which makes things much less complicated. And it's easier to optimize, more flexible, and more modular. So each of these passes then goes on to generate lower-level commands that are actually going to map directly to our graphics API, which is the piece of software that sits just above your GPU driver. And this backend collects and executes all of these instructions. And because there is no high-level knowledge of the rendering in this backend, it is just simply issuing commands. It ends up very simple and streamlined and much simpler than the equivalent on our old renderer. So the benefit of this simpler code is it's much easier to multi-thread, which is to say to run it on multiple CPU cores in parallel, something that is crucial for modern CPUs. So multi-threading is a complex and often misunderstood paradigm, so I thought it was worth us talking briefly about how we optimize multi-threaded code. And for that, I'm going to use an analogy of building a house, which is another complex engineering task with dependencies. So here you can see a list of tasks for a builder, a joiner, and an electrician, all running one after another, and there's dependencies between them shown in red. And in this example, the house is equivalent to rendering our frame. Each tradesman might be a different system, and then the capacity of 3 people in our house is equivalent to the 3 CPU cores we might have on our system. And the occupancy, as in the average number of people in the house, is effectively the same as the CPU or GPU utilization numbers you might see in Task Manager. So in this example, we can see the project takes 11 units of time and is on average 60% full for this house. Now, this occupancy of 60% isn't the direct reason that it takes 11 units of time, and that is in fact down to the critical path of work where the builder is blocking the joiner and the joiner is then blocking the electrician. So the obvious answer here is that you need another builder or multiple builders to work on this in parallel to unblock the joiner, and so on. You can keep on parallelizing this work to try and reduce the critical path. And that is our focus when we're optimizing multi-threaded code. However, not all tasks are trivial to run in parallel, and sometimes it's impossible to actually run them in parallel, so you'll end up with these unallocated capacity space and these bubbles. And in this case, if we imagine the electrician was in fact our GPU, then The fact that it takes longer is just going to result in a CPU bubble, which is unavoidable. And this type of thing happens very frequently if you have a configuration, for example, a very fast GPU and a very slow CPU, then unavoidably one of them two systems is going to have a bubble. So we can fill these bubbles with non-critical work like streaming meshes or textures, and this can help fill the unused CPU capacity. And this can be useful to try and get some extra work done, but ultimately it's not going to improve the performance of the frame. And the point I really wanted to drive home was that the CPU and GPU utilization, which are often looked at as key indicators of performance, aren't actually the direct thing we should be looking at. They are useful as statistics, but ultimately the frame time is the only thing that matters and the critical path that resulted in that frame time. So as we roll out Gen 12, we'll hopefully be putting some new statistics in there that the players can see to help them understand the performance and understand these bubbles, and that should hopefully give a little bit clearer insight into the performance of the renderer. So how we actually achieve this parallelism in practice, that's going to come down to two major changes. One is the architectural changes, which Christopher will talk us through, and the second is the Vulkan graphics API that Daryl is going to talk us through.
Welcome to the next section of our Gen 12 renderer presentation. My name is Christopher Bolte, Core Engine Architect here at Cloud Imperium Games, and I would like to spend the next few minutes introducing the high-level architecture of our in-development Gen 12 renderer. For this section, I will focus on the rendering of object instances in the world, for example chairs, walls, characters or spaceships. This part of the rendering pipeline is called scene object rendering and has the largest impact on runtime performance. There is also a lot of work happening on the architecture to manage operations which work on all pixels on the screen, so-called post effects, but I won't cover those. The current slide shows our existing renderer code setup. We have a main thread, which does all game simulation as well as figuring out what objects we should draw for every frame. And we have a render thread, which takes all those objects and translates their description into GPU commands to render them on the screen. The system is set up to double buffer the data. In other words, the render thread is working on data from the previous frame while the main thread produces data for the next frame. Such a setup allows easy performance improvements in some situations, but it also has two issues on modern hardware. First, the rendering code won't scale over multiple CPU cores, which can result in a bottleneck during execution. In other words, every visible object adds a certain cost. The more objects we render, the higher the cost. And as a single CPU processes this cost, no matter how well we optimize, at some object count we will run into performance issues. Second, since the main thread and render thread must be synchronized with vsync, we can end up with very bad load balancing. As shown in the slide, if the main thread takes longer than the render thread has to be idle and wait, and vice versa, if the render thread takes longer, then the main thread has to wait. During such wait time, the CPU is underutilized, especially if waiting for the single core render thread. One goal for the Gen 12 renderer is to remove this kind of bottleneck and instead architecture the system without those waits and allowing every operation to utilize all CPU cores. When we utilize all CPU cores, we would still have an object limit, as every visible object must be processed. But we can process a higher object count and at the same time reduce the latency on the main thread until all objects are processed, as we will be making better use of modern multi-core CPUs. Let's take a look at some details. For example, please keep in mind that the size of the sections are chosen to visualize the cost. Relation in size doesn't necessarily translate to the same relation in CPU cost. When looking at the cost of the operations done by the render thread, a pattern quickly emerges. We pay a similar cost for every rendered object. This is called a draw call. For every draw call, some time that is spent inside our own renderer code and some part of it is spent in the GPU driver code. In the next slide, we will cover our current process as well as the next steps to move the draw call cost out of the render thread onto multiple CPU cores. We already have a level of parallelization on the main thread, used to find out what objects are visible. There we use our batch worker job system. This is a parallelization system to execute the same code on a different object instance over all CPU cores. To give an example, checking 400 objects can be split over 10 threads, so that every thread will be processed 40 objects. By doing that, the latency on the main thread until all 400 objects are done is divided by the number of threads, reducing state latency to 40 objects only. Roughly at least. As in the actual system, several low-level factors affect the execution, making this statement not fully true, but covering those would be out of scope for this presentation. The visible check itself happens multiple times per object in a frame, as an object can be visible in the main camera, but it can also be visible in shadows, or via remote location rendering, the so-called render-to-texture or RTT rendering. The slides show those pairs as simplified, as we can have more than one shadow pairs, for example. Those visibility checks or culling operations are performed on all CPU cores with the batch worker system. When an object is determined to be visible, its rendering description is copied into multiple temporary buffers. Those temporary buffers are processed on the next render thread frame to submit every object's draw call to the GPU. In other words, object culling is already at the point where we want to have the draw call processing. Right now, we are in the first implementation phase. We have defined our low-level code building blocks, ensured our APIs work, and are now in the process of moving our own rendering code out of the render thread into the existing batch worker execution. This is a very time-consuming refactoring, as we need to change every rendering feature in a very old and large code base. But we have set it up in a way to allow us to gradually move over parts step by step. After this operation is done, we still copy state to a temporary buffer to be processed by the render thread. But the state which we copy is prepared in a way that we can directly send it to the GPU with minimal processing on the render thread. Doing this step will already give us performance benefits when we are render thread bound, as less code will be run on the render thread. Additionally, this is a necessary stepping stone for the next phase. After we manage to move our own rendering code to multiple CPU cores, we will start to utilize the Vulkan API. One major selling point of the newest generation of graphics APIs like Vulkan is the possibility to generate GPU commands on multiple threads. That is something which wasn't possible before, and mostly the cause for the existing renderer design. The catch is, to allow efficient parallel generation of GPU commands, the data must be prepared in a certain way. And that is what we are doing right now as part of porting the scene object rendering to Gen 12 and moving our renderer code to the batch worker system. When this is done, we can implement the parallel Vulkan backend and remove the render thread. After all that work is done, our renderer should be able to process a very high number of visible objects at lower impact on the frame time. At the same time, it will make better use of the available CPU resources and have less idle time when major systems wait for each other. Thank you for your time. Daryl will now take over to cover the Vulkan side of the Gen 12 renderer.
Hi, my name is Daryl. I'm a graphics programmer here at Cloud Imperium Games, and I work closely with Vulkan and our graphics renderer to make the game look as good as it does. So what exactly is Vulkan? Well, Vulkan is a modern graphics API that allows us as developers to take greater control over what you as a player sees and also affects performance greatly. As you know, we already have a few areas of bottlenecking on the CPU, but the design of Vulkan allows us to alleviate these bottlenecks by submitting work in parallel to the GPU. So I would like to explain a bit more about the software stack that's involved with our graphics in the engine. So from the image, you can see that we have a renderer front end, a renderer back end, and as well the graphics driver. The Vulkan API generally sits at the renderer back end and allows us a fine-grained control over what we develop and how we develop for it. It also gives us flexibility for cross-platform, including Windows and Linux, and anything we may want to look at in the future. The graphics driver stage is not managed by us, but we look at that and we gather information and process any crashes or any issues that might happen, and then we can deal with those further down the line. So you can see now how graphics APIs have changed over time. We're, of course, in the more modern section where Vulkan is on feature parity, essentially, with other APIs such as DirectX 12 Ultimate. You might also be wondering what a graphics API actually is, and we see that as a tool that is used for development that can interface between your graphics card as a player and us as developers so that we can give you the latest and greatest. Vulkan also has many features and extensions available to it that we will be exploring in the future, such as variable rate shading, bindless resources, and GPU accelerated ray tracing. To address any issues, we also need to collect data from our players' hardware so that we can use that to target specific features and extensions. We're not aware of any large-scale multiplayer games that captures Vulkan data live in the exact same way we do. Capturing this data allows us to plan ahead for any optimizations and then leverage that for the larger majority of players so we can bring you the latest and greatest. On screen at the moment is a diagram that shows the distribution available for Vulkan API versions amongst currently active players. This was captured in the last 3 months, and as can be seen, there is 98% of players that are able to use Vulkan fully in 1.2. We did see a negligible amount of 1.0 and some that were unavailable. We are actively looking into these cases, especially those that cannot currently run Vulkan as it is seen as unavailable. I'd like to take this opportunity to also say, please update your drivers, as we do see a few cases where this can take you straight to the latest version. I'd like to now explain a bit more about the render graph and how this works hand in hand with the Vulkan API in order to improve our usage of Vulkan. So a render graph can be seen as a collection of stages that depend on each other. This then determines the ordering, the scheduling, and the flow of the actual frame. This allows us also to then achieve any synchronization that we need to during that frame. It also helps us from a design point of view, as we can look at the render graph and see where there may be issues or potential optimizations. The render graph also allows us to keep track of any state of resources, and we can also validate against those resources as well. Now I would like to explain the render graph as a whole and give you an overview of how it works between the GPU and also how it works in terms of our frame. So a frame is made up of a collection of passes, and sometimes we require a texture to switch states, perhaps between read and write. The graphics driver used to do this for us, but now with modern APIs such as Vulkan, we need to carry out this work ourselves. What the render graph will then do is insert a pipeline barrier into the render graph and pass this work along to the GPU and switch the state. We can also cache the render graph and use any data we had from a previous frame or perhaps similar resources as an optimization. I'd now like to talk a bit about the synchronization that happens within the render graph and how resources change state. So the idea is that we want to switch the state of a resource as early as possible. We need to then also validate that this resource is in the correct state. So from the diagram, we can see that the depth prepass writes to image A, but then later on, we require to read from image A in the G buffer. So to this end, we insert a pipeline barrier for this transition between the two passes. These barriers are scheduled as GPU work, following a strict ordering dependent on other work that may have happened previously. All the work for a single stage within the frame can be carried out in a single pipeline barrier. I'd now like to talk about some of the more nuanced areas of our Vulkan implementation and how this affects us as developers and you as players. We use the DirectX compiler for our shaders, and this can compile our HLSL code into SPIR-V. DXC is a more modern compiler and has features that span both the D3D set of APIs and Vulkan. HLSL is a shader programming language that we as developers can utilize and read in order to make work happen on your GPU. This HLSL is compiled down then into SPIR-V. SPIR-V itself is not as readable, as it is seen as an intermediate language between HLSL and shader microcode. SPIR-V gives us less driver overhead at compile time. We can use this then to create our shader modules in Vulkan and optimize any dead code away. DXC also gives us shader model 6. Shader models have progressed over time in HLSL, with shader model 6 now giving language support for GPU parallelism, as well as variable rate shading, amongst many other features. We can see here now a diagram of how our shader compilation happens. It starts at the shader author level. This is where one of our many developers will write a shader using HLSL code with some markup integrated into that HLSL. This HLSL is then passed to the preprocessor. The preprocessor then removes any of the additional code that we don't need and is dealt with accordingly, whilst then outputting just HLSL code. The HLSL code is then passed to DXC, and DXC will change this into SPIR-V. It's at this stage that we can carry out any additional compiler optimizations and improve compile time performance even more. SPIR-V is then passed to the driver, and the driver will then change this into microcode, which will run specifically on your GPU hardware. As I've previously mentioned, there have been several Vulkan core versions over time. Each one has added new features and extensions for us to reach into and develop with. Two of these I'd like to explain a bit more in detail now that we would like to look into and develop for in the future. These are both bindless resourcing and also fragment shading rate. Fragment shading rate can be seen as the same as variable rate shading, as you may have already seen. What this does is works on groups of pixels instead of a singular pixel at a time within the shader. This allows less overhead in the frame, whilst at the same time allowing variable amounts of these groups, including variable sizes, in order to have less fidelity where may not be as important to look at. Bindless resourcing is where we can take large groups of textures, for example, and reach in and grab one of these inside the group. This gets rid of the overhead of specifically binding two slots within the shader. This also extends to other resources, including buffers. I'd now like to talk a bit about the video RAM involved in your graphics card. VRAM used to be managed by your graphics driver, but with Vulkan and other modern APIs, this is now managed by the developers. There are existing solutions towards this. However, we have decided to use our own implementation. This is because we know exactly what resources are used upfront and how much memory these resources use. Using this, we can potentially beat what the graphics driver used to be capable of. As we know all of our resource life cycles, we can take advantage of that. From the diagram, we can see memory being paged in and out as it used to be when it was managed by the graphics driver. On the other side, we can see memory being allocated and then suballocated, and we can then offset into the data from this suballocation. The memory paging of years past could potentially result in a performance loss, because this was seen as a more one-size-fits-all. We, of course, want to avoid any of that performance loss and the memory cost involved by offsetting into these larger buffers. This can also help mitigate cache misses. This then leaves us with all of the allocation, freeing, usage, and reusage of resources. I'd now like to pass you back to Alistair Brown, the Director of Graphics Engineering.
Following on from what Dowell explained there with the explicit memory management in Vulkan, we're intending to expose some of this memory management to the player through the advanced graphics options. We're going to let you tweak the memory assigned to each system so you can balance the preferred visuals and performance for your experience. For example, you may want to balance the output resolution of your game to a higher resolution, but then sacrifice some shadow quality. Or maybe you want to use a lower internal resolution and rely on upsampling to achieve higher texture quality. These options will all be available to you, and obviously only capped by the hardware that you possess. So to summarize, with our Gen 12 renderer, we're hoping to achieve something that is more efficient, modular, flexible, and minimal abstraction to the hardware, and uses modern graphics APIs like Vulkan. So now you know a bit more about what Gen 12 is, I'll try and let you know where we're up to. So we've done a huge amount of work already. The architecture is all in place, and we're using this hybrid rendering approach where we're combining elements of the old and new render at the same time to allow us to move piecemeal to the new system. All of the post effects, fog, and lighting have been converted over, and they're all enabled by default in 3.15. And the fundamentals of scene and geometry rendering are all in place, but they're still being worked on. So our main focus is finishing that off at the moment, and once that's done, our focus will shift to the remaining major systems, which are gas clouds, the render to texture system, and a few special cases for transparency. After this, that's where we'll start seeing the public milestones, and the first of that will be 100% usage of Gen 12 and none of the hybrid approach. This will still be at DirectX 11, our current graphics API at this point. And then our second milestone will be the Vulkan API release. That will be optional at first and then mandatory after we've removed all the bugs. And then our final milestone will be when we have performed the optimizations for multi-threaded. So that will only happen once the Vulkan is in place and we can finally look at the performance on the final graphics API and optimize all the remaining code. So after Gen 12, I just briefly wanted to touch on what comes next for the graphics team. So a lot of Gen 12 has been focused on CPU performance. So after Gen 12, we really want to start looking at the GPU performance. The first few things we'd look at here were things that wouldn't change the visuals, just improve the frame rate. Things like DLSS, FSR, async compute, and variable rate shading. After we've improved this GPU performance, we want to start looking at some of the more exciting visual features. So then there is also mesh shaders and primitive shaders, which is technology we can use to generate procedural geometry. And this type of thing could be really exciting for things like the planets or asteroid fields where procedural geometry is critical. And then there's the big one, ray tracing. We're very excited to get onto ray tracing, especially to use it for lighting, such as global illumination, but also reflections and shadow quality. There's a lot of exciting areas for us to look into, and we can't wait to get into it. So that's it. I just wanted to say a big thanks to everyone that's been involved in this technology. It's involved the graphics team, engine team, VFX, and Planet Tech all working together on a huge piece of code. And we can't wait to get it into your hands as soon as possible.